Hello everyone. So this is our 8th live session of the course Semiconductor Devices and Circuits, and today we are again going to solve the problems associated with the previous assignment that was that has already been submitted by you. So we will begin by uh, solving a problem associated with PN junction, and then we will move to the bipolar junction transistors. So I guess we should start today's session, and let me turn off the video. Okay, so let me start with a simple problem statement. So, okay, let us do the BJT problems after this, and let me bring one kind of a PN junction. Till now, what we had seen previously is that we saw that the abrupt kind of a PN junction, that is, the junction transitioned from the impurity concentration, let's say on one side, on P side was acceptor, and on the donor side was uh, on the N side was donor impurities, and the transition at the interface was abrupt kind of a thing. So by abrupt, what I mean, if I draw the abrupt junction, sorry, if I draw the abrupt junction, the 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 impurity concentration from the P region, if this is our interface, let's say, and this is my P region, okay, this is my P region, and this is my N region, and this is our interface, okay. Then the depletion charge, if this axis is the depletion charge, you must have seen this kind of a profile in the lectures itself. The professor was teaching us these kind of a things, and this is the acceptor impurity, and it extends to the minus WP, which is the depletion width on the P side, and it will be acceptor impurities. Okay, let me draw it like this, minus minus. And similarly, we will be having donor impurities, minus plus WN on the P side. Okay, so what does this profile also signify? It signifies something. What we have drawn over here is that since the depletion region WP is less than the WN, it clearly shows that the material is more P-type. P-type doping is high as compared to the N-type doping. Okay, that's also being inferred from this, what you can say, from this charge depletion charge profile. So this is an abrupt junction because the impurity concentration, the impurity concentration changes abruptly, changes abruptly from acceptor, that is Na, to donor. Okay, that is Nd. So you can clearly see this transition over here, over this interface, that we are having abrupt transition. Okay, sorry, abrupt transition. Now this is quite, or can say, this is not quite possible in real world scenarios to have such kind of a transition. In practical or in the real life PN junctions, what we would see is, sorry, what we would see is we will be having abrupt kind, we would not be having this abrupt kind of a junction. Okay, instead of this, the doping profile will change kind of a linearly. Okay, so this is not kind of a thing that would happen. It can be linear or some other function with with the distance near the metallurgical junction. So so this depletion width will can be approximated. This the doping profile can be approximated by a linear function. And we can say that if we want to solve for the electric field and the built-in potential and the potential for that linearly graded junction, we need to start right from the basics, that is the Poisson equation. Okay, so it means that if I draw this linearly graded junction, it means that the doping is not changing abruptly from the n type, sorry, from the p type to the n type. So the transition is kind of a linear near the metallurgical junction, and the doping profile will look like, let me draw this, let me say it is a linearly graded junction. So it is a linearly graded junction, and the profile will look like, if I draw this to be the depletion charge, sorry, this is my depletion charge, that is Nd minus Na. So most of the notes that I am going to teach today will be from the SMZ, the book I had mentioned previously, which I recommended you also, that you should have a bit insights about that book after doing this course, which is being taught by professor. And if you are able to grasp the concepts for whole concepts from this course, then you will be able to understand the real depth of the book. Okay, that is the physics of semiconductor devices by SMZ. Okay, so I am also teaching these things from SMZ today itself. So if this is our depletion recharge profile, and it would look like, if this is the distance, considering that the interface, the metallurgical junction, we have to consider the linearly graded junction. So this will be the minus WD by 2, this will be WD by 2. So this is ND positive, this is ND positive, this will be negative, 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 and negative. Okay, so this is how the depletion charge profile will look like on the N and the P region. So this is our P region, and this is our N region. Okay, now what we have to do is, we have to, if we want to solve for the electric field, the charges, we need to solve for the Poisson equation. Okay, so the Poisson equation needs to be solved. Okay, in order to get insights into the electric field inside the junction, and also the potential variation within this PN junction, which is kind of a real, this is a real, sorry, what is happening with this, real devices. So it is prominent in real devices. Okay, so the Poisson equation needs to be solved for these, and if we solve for the Poisson equation, we know The Poisson equation is simply d square psi, let me write it psi I dx square, because the notations are almost similar to that of the SMC, is equal to d psi by dx, which is the Gauss law, is simply rho x, which is the charge, divided by epsilon s, which is the relative permittivity of the semiconducting material. Now, the charge rho of x is simply q times p minus n plus a x. Okay, so this a is the doping gradient, and its units, a has units of centimeter minus 4, because a times x is centimeter minus 4 into centimeter, so it will be centimeter minus 3. Okay, so the units will be of this whole quantity ax will be centimeter per centimeter cube. That's what we need to have. So the units of this a will simply be centimeter to the power of minus 4. So now we can assume, or we can approximate this rho to be linear. Okay, near the, since this p and n, we can say that since this is the linear function of x, we can simply say it is simply q a times x, this rho of x. Okay, so from this, if I now solve for the this charge, and integrate it for the field, that is d e of x by dx is rho of x by epsilon s, it would simply be, it will approximately be q times ax by epsilon s between the depletion width, okay, which was wd by 2 to wd by 2 minus wd by 2 to plus wd by 2. So the electric field, what we would do, we would integrate with respect to x, is simply qax dx by epsilon s. Okay, so it will simply be qa by epsilon s, okay, x square by 2 plus some constant c. Okay, now we know that the electric field at the depletion region edge has to be 0. That is, the electric field at depletion region edge has to be 0. It has to terminate, because we know that the bulk of this material will be free from the any kind of a field. So this is a valid approximation. So we can say clearly that the electric field at WD is 0, and this is QA by epsilon s by 2. This is x square, which is WD by 2 whole square plus c, or simply the value of the constant is minus QA by 2 epsilon s WD by 2 whole square. So this is the value of the constant c, and from this we can obtain the electric field. So we can obtain the electric field simply, which will be E of x is simply this qa epsilon s x square plus c. So if I take this minus qa by epsilon s, so it will be qa by 2 epsilon s x square. C is having the value of minus qa by 2 epsilon s, a by 2 epsilon s, wd by 2 whole square. Okay. Now, if I this will be between wd by 2 to wd by minus wd by 2 to plus wd by 2, or simply if I take this minus qa by 2 epsilon s common, it would be simply wd by 2 whole squared minus x square between minus wd by 2 to wd by 2. Okay. And also we know that the electric field will be maximum at the junction. Okay, because the maximum field lines pass through that region. Okay, so field, this can also be verified. Field is, so the field is maximum at x equal to 0. Okay, so we have been able to find the electric field for this linearly graded junction, linearly graded PN junction, which is the case in the real or practical devices. So now we have got the electric field. From the electric field, we know now this is a quadratic function of the x. So if I draw the electric field with respect to x, since it is having the value of, it will be having 0 value at uh, wd by 2 plus minus wd by 2. So let me draw this over here. So if this is my x, this is my field, and this is my interface, and this is x equal to 0, where the field will be maximum according to this relation. So, and the field will be 0 at minus wd by 2 and wd by 2. So we can clearly see that the electric field profile will look like this, with this being the maximum value. Okay, so this will be the maximum value, this will be negative, so this will be maximum magnitude value. Okay, and this maximum value is simply given if I put x equal to 0 in the previous expression. So if I put x equal to 0 here, it will give me magnitude of the maximum field, and it will be simply qa by 2 epsilon s wd square by 4, or simply it will be qa wd square by 8 epsilon s. So this is the maximum field, and this is the value of this. So it will be simply qa wd square by 8 epsilon s minus times. Okay, so this is the maximum magnitude of the electric field. Okay, that we will get for this linearly graded junction. Now from the field we can calculate the potential variation within this linearly graded junction, and it will simply be, if I draw this thing, it will simply be, if I now solve for the potential, it is simply minus d psi of x by dx. Now integrating this expression which was obtained for the electric field, it will simply be, because the area under this area under this electric field curve will give me the built-in potential. Okay, built-in potential. So this minus d psi by dx, if I integrate now this expression which was obtained by solving the Gauss law, and now we are going for the Poisson equation, 2 times epsilon s wd square by 4 minus x square. Okay, so this minus and this minus will go, and we will simply integrate this thing. This will be d psi of, so this will simply be psi I of x. If I integrate this thing, it would be simply qa by 2 epsilon s wd square by 4 minus x square dx. So if we integrate now this, it will be simply psi I of x is simply qa by 2 epsilon s, qa by 2 epsilon s times wd square by 4x minus x cube by 3 plus the constant c. Let's say it is c1. Okay, this time. So it is c1. Now this is the value of the psi I between, sorry, it has to be between minus wd by 2 to wd by 2. Okay, so we now have to find the potential variation, and we know at minus wd by 2 we have to take some point as a reference. Okay, we say the potential is 0. Okay, and we put this in the expression above, minus wd by 2, it would be simply psi of minus wd by 2 is equal to 0 is equal to qa by 2 epsilon s, it is wd square by 4 times minus wd by 2 minus times minus of wd by 2 cube by 1 by 3, okay, plus c1. Or we can simply say, if I take this common, this is simply minus times qa by 2 epsilon s, this is minus times wd cube by 8, this is plus times wd cube by 8 by 3, or simply it is, if I take minus qa by 2 epsilon s wd cube by 8 common, this is simply minus 1 plus 1 by 3. So it's minus 3 plus 1, so it is minus 2 by 3. Minus and minus will go, so it will be qa by 2 epsilon s wd cube by 8 times 2 by 3. Okay, so this is what we have got from the, for the value of the constant c1. Now let us put the value of the c1 again in the expression, in the this expression. Let me encircle it in red. Okay, let me encircle it in red. We have to put the value of the c1 over here. So the psi of x, so the psi of x will simply be, psi I of x will simply be, will be qa by 2 epsilon s 2 epsilon s Okay, WD square, yeah, I guess it is WD square, WD by 2 whole square times x minus x cube by 3, I guess. Yes, minus x cube by 3, minus x cube by 3 plus C1. C1 is having the value of QA by 2 epsilon s, QA by 2 epsilon s, that we have taken as common. So it will be plus WD by 2 cube, okay, 2 by 3 times 2 by 3, okay. Or simply, if I take 3 as common, it will be simply QA by 2 epsilon s 3 times WD by 2 whole square x minus x cube plus 2 times WD by 2 whole cube for x lying between minus WD by 2 to WD by 2. Okay. Now from this we can also calculate the built-in potential, and the built-in potential, now we have taken the minus WD by 2 as the reference, so the built-in potential will simply be psi of I at WD by 2. Okay, so it is simply, we have to put WD by 2, so it will be QA by 2 epsilon s 3 times WD by 2 whole square into WD by 2 minus WD by 2 cube plus 2 times WD by 2 cube. So it is simply 3 plus 5, it is 4. Okay, so it is 4. Sorry, it should have been 6 over here because I have taken 3 as a common. Okay, it has to be 6. Okay, so it is simply 4. So it is QA by 6 epsilon s times 4 times WD by 2, or simply this phi bi is QA by 6 epsilon s. This 4 will go with this WD cube by 8, and we will be left with WD cube by 2, or simply phi bi is QA WD cube by 12 times epsilon s, or the depletion width WD, we can simply write it to be equal to 12 times epsilon s phi bi by QA raised power 1 by 3. So this is the value of the depletion width for the linearly graded PN junction. Okay, so what we have been able to achieve is, we have been able to follow what I said was that for an abrupt PN junction, when we are transitioning the impurity concentration from the acceptor to the donor, this is not physically possible in the physical devices. So instead of this kind of a profile which was shown over here, over this region, that is abrupt change, we said that is a change in the doping variation or in the impurity concentration will be linear instead, and we will be getting some profile which will look like this. Okay, near this PN junction, metallurgical junction. Okay, so from this we were able to solve the solved for the Poisson equation for this linear profile, and we looked how they how we can obtain the electric field, and the electric field came out to be as a square function of the distance. Okay, and we looked into the maximum electric field, and its value was somewhat square of the depletion width. Okay, that was qa wd square by 8 times epsilon s. And then we said we have to solve for the Poisson equation, and we solved for the potential, and we got the potential to be as a function of cubic function of the position. Okay, and from that we solved for the built-in potential by taking the side on the p side potential as the reference, and we found out the value of the built-in potential was somewhat cubic function of the this depletion width. Okay, what we have considered in this case, was that the doping on the n and the p side is of the same. That's why I have taken minus wd by 2 on the p side and plus wd by 2 on the n side. So the case can be, both the depletion widths can be different, and in that case we will be having different different WD, different built-in potential, which will be a function of WDP and WDN, and also the electric field will also be function of the WDN and WDP. So this was a simple case where we solved for the real metallurgical kind of a interface, where the transition was not an abrupt kind of a thing, but it was the linear kind of a thing. So this kind of problems or these kind of concepts are usually the advanced kind of concepts that are mostly taught or mostly asked as advanced level problems in gate examination. Okay, so this was one of the case which one should be aware how to solve for any charge profile. If we are given the charge profile, how we can obtain the related field and the related potential variation by just solving the Poisson equation, Gauss law. So this was one of the practical applications of this linearly graded junction region. Okay, so we could have solved for any arbitrary profile as well, considering any arbitrarily doping profile, but that would be much what you can say, that will be a tedious effort for us, so we should not go into that. But still, considering the fact that this linearly graded junction, this is a good problem for you to solve by yourself again. Even if you do not know anything, this will help you to build the concepts related to the p-n junction and the interfaces. So now let us move to the real topic which we had to study after this p-n junction, which is the BJT one. Okay, so let's go into the BJT problems itself. So you know that this BJT, it basically can be of two types, mostly what we say, that is NPN and PNP, and you have seen that we can connect this BJT in three different configurations depending upon the which lead is common to the this input and the output, and we can have the common base, common emitter, and common collector configurations, and we will be having this current IV, that is current and voltage relationships based on the how we bias the base emitter junction and the base collector junction. So for most of the cases, we can say that the regions, if we dope them, that the emitter is highly doped, and the regions, the collector is the lowest doped. Okay, so for the normal operation, what we have is we have two junctions. One is at the base emitter PN junction, and other is the collector emitter PN junction. Okay, so we need to control these two PN junctions for the in order to operate the device. So if we consider the forward active mode, we say that that is the normal operating condition of any on any BJT. We say that the transistor, which is the PN junction, which is at the base emitter side, will be forward biased, and the junction which is at the base collector junction will be reverse biased, in order to sweep all the carriers that are coming from the emitter directly at the collector. Okay, so we will be having this collector region, which will be having larger depletion width as compared to the base and the emitter, and this will be reverse biased this base collector junction, and as a result of the reverse bias of this base collector junction, the field will be high, and as a result the carriers that will be coming from the base emitters this emitter side into the base will be directly swept to the collector. And also another condition on the base will be that this base region should be narrow. Okay, it should be we will have a problem that what should be its length. What it is associated with the diffusion of the carriers, that is the carriers that are moving from the emitter to the collector. So we will see that problem also. So now we can say that there will be different components for this current, and if we consider this base emitter junction, which is forward biased, the PN junction in the base emitter is forward biased, the current for example, let's say the NPN junction, NPNP transistor, the electrons will be diffused from the emitter into the base, and from the base they will move to the collector. Okay, so this base will act as a barrier to the electrons. Okay, and you need to have this base region to be very less than the diffusion, or than the diffusion length of for these electrons, in order to have no or less the recombining of the electrons in the base region. And you can say that the injection ratio of the electrons will be higher. Okay, we need to have the injection ratio of the electrons to be on the higher side for this we can say this NPN junction kind of a thing. Okay, so basically BJT is nothing but two diodes. Okay, we have to consider two PN junctions. One is forward bias and another is reverse bias, for the sake of the convenience. Okay, one will be for the forward, this normal mode of operation, one will be forward bias and another will be reverse bias. So the problem now is associated with the BJT itself, and it says that the parameters for the base region in NPN BJT, that's what we were talking about. For NPN, the electrons will be the majority carriers in that we need to collect at the collector. Okay, we need to transition from the base region where these electrons will be minority carriers, and we need to have the minimal recombination in the base region. Okay, so this Dn is the diffusion of the electrons, diffusion coefficient of the electrons in the base region, and B naught, it should be 10 to the power of 4, it should not be 104, it is 10 to the power of 4 per centimeter cube, and the area of the base is given to be this, and the base width is given 1 micron, and we need to find the value of the collector current when the base emitter is voltage is 0.6 volt. Okay, and when the base collector junction is reverse bias. So this is the normal condition that we have. So the base collector junction is reverse bias. Okay, now the collector current, it can be simply given. I see you must have gone through these things, is Q times the area times Ni square by, this will be divided by the base width by NAB, whereas NAB is simply the minority. We will relate this expression to the minority carrier concentration times dN, which is a diffusion of coefficient of the electrons, exponential of Q times VBE by KT and so on. Okay, so this thing is simply equal to NB naught, which is the minority carrier concentration in base. Sorry, what has happened with this thing? Okay, let me write it again. It is NB naught and it is minority carrier concentration in base region. Okay, so the IC will simply be Q times A times by XB times dN times NB naught exponential of Q times Q times VBE by KT minus 1. Okay, now let's put the values and let's try to solve for these. A Q is 1.6 into 10 to the power of minus 19 times the area is 10 to the power of minus 4 centimeter square, and the value for the this dN is 20 centimeters square per second. So it is 20 times the NB naught, minority carrier in the base, which is 10 to the power of 4 per centimeter cube, divided by the base width, which is 10 to the power of minus 4 centimeter, because it is in micron. It was given to be 1 micrometer, and 1 micrometer is 10 to the power of minus 4 centimeter times exponential of VBE. VBE is 0.6 and KT by Q is 26 milli electron volts, so it will be 0.026 minus 1. Okay, so let's solve for this. It has to be exponential of this thing, then this, and we will be getting this to be equal to approximately 33.6 into 10 to the power of minus 5 amperes. Okay, the answer is in milliamperes or microamperes, so it is simply 0.33 milliampere. So it is simply option B. Okay, so this is the correct option to go with. Now moving to another problem, which says that we have to consider the base transport factor to be equal to alpha t, and alpha t is given by a function which is cos of 1 by cos of xb by lb, where xb is the base width and lb is the minority carrier diffusion length. Okay, and we have to find out the base width in a PNP BJT to achieve a transport factor of 0.9967, and the diffusion coefficient value is given to us, and it has been given to be equal to 10 centimeter square per second, and the minority carrier lifetime in the base is given to be 10 to the power of minus 7 second. So it is simply a mathematical problem, not more than that. So the alpha t is simply given to be equal to, it is given 1 by cosh of xb by lb. Okay, so it has been given to us, and from this the alpha t is given to be equal to 0.9967 is equal to 1 by cosh of xb by lb, or simply it will be cosh inverse of this thing. This will be xb by lb. Let me solve for this, and it is simply coming out to be equal to 0.0814. Okay, but this lb, this minority carrier diffusion length in base, is simply given by the diffusion constant in the base times the minority carrier lifetime, which is tau b. Okay, so it will be simply, this will be simply 10 into 10 to the power of minus 7, and it will be simply 10 to the power of minus 3, okay, centimeter. So this is the minority carrier diffusion length in base, and this is the minority carrier lifetime in base, and this is the diffusion coefficient. Okay, so that is what we have got, the value of the lb, and from this base width can be given xb times 0.0814 times lb, and it is simply equal to it will be simply equal to this lb, which is 10 to the power minus 3 centimeter, and it will be 0.0814 into 10 to the power of minus 1, so it will be 0.81 micrometer. Okay, so this is the value for the base width we are going to get. Now moving to another problem, which says that in a BJT in active mode, the base current is given and it is equal to 6 microamperes, and the collector current is 510. So we have to find the value of the alpha. Okay, we have to find the value of the alpha, but we know the beta value, which is the ratio of this collector and the base current, is simply beta times IB is IC, or IC by IB is beta, and it will simply be the 510 divided by 6. It is simply, it will be 85. Okay, and we know alpha is simply beta divided by 1 plus beta. The alpha value is always close to 1. Okay, so it is simply 85 divided by 86, and it is approximately equal to 0.988. For the better efficiency, we need it to be tending to 1 always. Okay, so which of the following statements is true? And as we said, the collector has to inject the electrons or the holes, considering the PNP or NPN side and BJT, that is, it has to inject the majority which is in the emitter side. Okay, so the emitter has to be heavily doped for that. So this statement is split that the emitter will be heavily doped. Okay, so and now moving to another problem, which is as simple. Now another simple statement problem, simple statement problem, which says that which of the following statements is true with regards to BJT, the first statement is the base width must be designed to be much larger than the minority carrier diffusion length, which is absolutely wrong, because if the base width is much larger than the minority carrier diffusion length, we will be having the carriers that will, for example, if you have NPN transistor and the electrons are moving into the base, and we will be having these these carriers, which will be the majority carriers on the emitter side, and when they go on the this base side, they will be annihilated, and we will be having the, we can say, decrease in the number of the carriers, which we do not need. Okay, we do not want the carriers to recombine in the base region. We want the carriers to move directly from the collector region to the from the emitter region to the collector region without being recombined in the base region. So for that, we want the base width to be smaller than the minority carrier diffusion length. So the option B is the correct option to go with. That's what we have written here also, that the diffusion length is average distance traveled by minority carrier before recombination, and we want minimum recombination in the base region. Okay, we do not want the recombination to happen over the region. So we generally design the base width such that it is less than the diffusion width of length of the minority carriers. So the chances of the recombination are reduced. Okay, that's why we will be having it base width to be smaller than the diffusion length, minority carrier diffusion length. The minority carriers in the base will be the majority carriers of the emitter. Okay, let's be clear of these things. Okay, the emitter emits, let's say for NPN transistor, emitter will have the majority as the electrons. The electrons in the base region will now be the minority carriers. Okay, we do not want them to recombine in the base region, so that's why we will design the BJT such that the base region will have the length which will be smaller than the diffusion length of the electrons. Okay, the diffusion length of the electrons. Okay, now this concept is associated with the early voltage, and it says that what does the early voltage represent. Okay, so if we draw the collector current with the collector emitter voltage, we will get the characteristics like this. Okay, we will get the characteristics like this. Had it been the ideal, we would have got the saturation kind of a thing for all the curves like this, but there is also the output impedance associated with the devices, and which we can say is like this. In the forward active mode, the output conductance is associated with the device, and as a result of this thing, this has been attributed to the base width modulation. And we can say that since this is not the case in practical devices due to the base width modulation, we will be having some slope in the curves. Okay, the slope is like this. Okay, it is not ideal, it is not ideally saturating, and we are having some slope, and these lines, they all, if we extend them to the negative axis, and they will all intersect at a point which is known by the name of the early voltage. Okay, so this is what we say, that the curves on the collector current characteristics intersect the voltage axis, and when extrapolated to zero collector current value, we will get the value for the early voltage. Okay, so the option C is the correct option. So these are the statements. Okay, now the base width modulation, what we saw previously, it results in the output conductance of the device. It results in the increment in the output conductance of the device, as it's evident from these figures. Okay, over here for different VBE, for we will be having these slopes. Okay, so the slope is simply the resistance R naught. Okay, and 1 by R naught is for the all these, this slope will be 1 by R naught, and R naught will be the resistance, output resistance associated with these things. So this is the as this base width modulation increases, we will be having this output conductance increment. So These were some simple statement problems which we had seen. Now we have another problem which is associated with the BJT, and the BJT is having some base width which is given by 0.5 micrometer, and this is given to us because we need to find the punch through. We have been given the punch through condition. We know that if the punch through happens, then the collector and the emitter region, they will be touching each other. Okay, the space charge, for example, we will be having space charges on the base region and on the collector region, and the what would happen at the punch through is that the depletion width will be wholly covered by these space charge regions, and we will be having the collector and the emitter sides kind of a touching or contacting each other without the you can say the influence of the base region. Okay, the base will be kind of a gone in that case, and we will be having kind of a emitter and collector touching each other. So if we say that for this we have to find the collector doping concentration, so let us write it like this: NC and NB are collector and base doping concentrations, and this if we consider now let me draw it like this, that if this is my base and this is my collector, let's say, okay, and this is the interface, and this is the depletion width on the base side, let's say, and this is the depletion width on the, let's say, on the base side, and this is my, if I draw the emitter as well, okay, and this is my emitter, and this is the total base width, the x1 has to extend to the depletion width. Okay, that is the x1 has to be equal to, x1 has to be approximately equal to WB for punch through. Okay, for punch through condition, this is approximate. Okay, because we will be having depletion width in this region as well, but for the sake of the mathematical convenience, what we would say that all the x1 will be, it will be all the x1, the xwb, considering the base collector region being reverse biased. Okay, so we would say that we would say, since this x1, which is the depletion width on the base collectors region on the base side, will simply be 2 times epsilon naught epsilon r, which is our simple formula, divided by VBI Br, which we got by solving for the PN junction, and this was done through the Poisson equation, Nc by Nb 1 by Nc plus Nb. Okay, this whole is under the square root, and we know at Vr equal to V punch through, x1 is equal to, approximately equal to, depletion width. Okay, this will be at the punch through, and also this VBI will be much less than this V punch through. Okay, V punch through, and it is given also over here, it is given in this problem as well, because VBI will be much less than 25 volts. So if I use another color, and if I say it like this, it will be simply, now if I square both sides, it will simply be Q, it will be x1 is WB now, So it will be WB square Q times NB times NB plus NC, okay, divided by 2 times epsilon naught epsilon S times NC. Okay, this will be the punch through voltage. Sorry, this will be our punch through voltage. Okay, yeah, it will be our VR, and VR is V punch through, VPT. Let me write it as PT. Okay, so we need to solve for these things, and let us solve for this. So it is 0.5 into 10 to the power of minus 6, or 0.5 into 10 to the power of minus 4 times 1.6 into 10 to the power of minus 19, okay, times NB. NB is 10 to the power of 16, and it is 10 to the power of 16 plus NC. Similarly, putting the values of these 2 times epsilon naught epsilon r and NC equal to 25, we will get the value of for this NC. Okay, so it's now a simple problem of the mathematical problem. So let's move to another problem. So we have to find the depletion width of the collector. So it will be simply x2, which we saw in this region, and x2 will simply be given by 2 times epsilon naught epsilon r, this V punch through, NB by NC, okay, 1 by NC plus NB by Q. So we just need to put the values from the previous problem, and we will get the value of this depletion width on the collector side. So these are quite straightforward problems, considering that we just need to do the mathematical analysis. So let us move to another problem, which says that we have to consider a uniformly doped NPN junction, and this NPN BJT is having some specifications. That first of all, it is in forward active mode, that is the base emitter junction is forward biased, and the collector base junction is reverse biased. So this is the normal mode for the BJT, and the collector base junction is reverse biased, and the bias voltage is 3 volts, and the metallurgical base width is 1.1 micrometer. Okay, the base width, the emitter and base and the collector doping concentration are given, which is 10 to the power of 17, 10 to the power of 16, and 10 to the power of 15 for the for this transistor, NPN BJT transistor. Okay, and now we have to determine this base emitter voltage such that the minority carrier electron concentration at NB, that at x equal to 0 is 10% of the majority carrier hole concentration. Okay, so what we need to do is we need to have the value of the NP naught, which is the minority carrier concentration, is simply Ni square by Nb. Ni square is simply 10 to the power of, Ni square is, it should be 1.5 into 10 to the power of 10 square divided by the Nb is the base, the majority base doping, the majority concentration of the holes, which is 10 to the power of 16, and 1.15 into 1.15 is simply 2.25 into, it will be 10 to the power of 4 per centimeter cube. So this is the minority carrier concentration of the electrons on the on this in this p side. Okay, so it is simply, now what it is, at that would we have been given that at x equal to 0, that is at np of 0, it is simply np0 exponential of vbe by vt. Vt is the kt by q simply. Okay, or simply vbe is vt times ln of np of 0 by np0. So since np of 0 is 10% of, is 10% of majority carrier concentration of holes. Okay, it's given in the problem, it's 10%. So it is 10% of 16, so it is 10 to the power of 15 simply centimeter cube. And VBE is simply 26 millivolts times ln of NP of 0, it is ln of 10 to the power of 15 by 2.25 into 10 to the power of 4. So it is 10 to the power of 10, 10 to the power of, it is 10 divided by 2.25, 10 divided by 2.25, 4.44, ln of 4.44 into 10 to the power of 10 into 26, so it is 663, it is 0.637 volts. So this is the base to emitter voltage that is required. Okay, so it is approximately option A. Okay, approximately this option is the correct 0.637. So what we have done is we have solved some of the problems associated with the BJT that were mostly so considering what we had done previously, that is the PN junction. We just said that it is nothing but one PN junction forward biased and other PN junction reverse biased for the forward active mode. That's what we saw for all the BJT problems. Okay, basically we have to consider two PN junctions for all the BJTs. Okay, and we will be making our life easier because we now know the PN junction, sorry, really well. We can easily say that the BJT is nothing but two PN junctions in conjunction with each other, and depending on the biasing of these PN junctions, we will be having different modes of operation which the professor taught us. Okay, now moving to another problem. Uh, before moving to another problem which is associated with the MOSCAP, I should first start giving some insights about the MOSCAP, because I guess the assignment deadline is not over yet for the MOSCAP. So if we just see what this MOSCAP is, this, sorry, this problem over here is for the NMOSCAP for the CV. Okay, so basically MOSCAP is nothing, it is it is a two terminal MOSFET device, not MOSFET device, two terminal MOS device. There are no source and drain terminals for this. Okay, so this MOSCAP, let me write it like this MOSCAP, it is a two terminal structure. Okay, It's a two terminal structure. Okay, so let me draw it like this. Let me draw a box to get some physical insights about this thing. First of all, we will be having a gate. Let's say it's a metallic gate. That's why metal. Then we are having this oxide, which is insulator. Okay, and then we are having this semiconductor. Let's say it's p type, because I will be drawing the band diagram. It can be n type as well, but since I am drawing the band diagram for the p type configuration only, and there will be also the back contact. Okay, this is back ohmic contact. Okay, so that's why we are having two terminals. This is body contact kind of a thing, which is back contact, and this is gate kind of a thing. Okay, so we are having two terminals. One is the gate and other is the body. That's why the name two terminal. Okay, we said it is MOSFET because it is having this metal, it is having oxide, and it is having semiconductor. That is why MOS. And it is a capacitor. You must have seen, for example, if I have a metal plate and between I put some dielectric, and I have another metal plate, the system overall acts as a capacitor. Okay, that's what we had seen in the high school as well. Okay, in our 11th or 12th class, the system how we make the capacitors, and it was the two metallic systems separated by some dielectric, and that's what it is over here. Instead of another metal, we are having semiconductor. What we need basically is we need another plate or another material where we can reflect for the charge change which is happening in the metal side or on the one terminal. Okay, you must have seen, for example, if we charged one metal plate to be positive, another was the negative, and as a result we would have the electric field lines terminating from the positive on the negative charge and giving rise to some capacitive behavior. So it behaves like a capacitor. Okay, more of like a capacitor. That's why we call it by the name of MOSFET. Now if we draw the band diagram for the ideal MOSFET, what it should look like. Okay, so for the ideal MOSFET that is having no metal work function difference, metal semiconductor work function difference, and also considering no oxide charges, we will be having the band diagram. If I draw the vacuum level, it will be a straight line. I'm sorry for this. Let me try to be more precise with my drawing. Please consider this to be a straight line. So this will be the vacuum level. Okay, on the metal side we will be having some metal work function. Sorry, we will be having some metal work function which will be given by Q phi m, and also we will be having oxide. This is the Fermi level. Okay, the Fermi level has to be constant throughout, and since we are considering this to be ideal with phi m equal to phi s, we can say that this is the Fermi level of the semiconductor. We are considering an ideal case. Okay, and this is our since this was the p type, the valence band will be closer to the Fermi level EV. Let me say this is p type. That what I had said previously. I had said we will draw for the p type. This will be my intrinsic Fermi level, which will be above the Fermi level for the p type, and this will be the conduction band edge. Sorry if I have drawn it too close, but I had to because I have to show that this is the oxide. Okay, this is our oxide, having some electron affinity. This is our silicon dioxide, and this is the barrier for the silicon dioxide. Okay, barrier for electrons. Okay, and this is the electron affinity for the semiconductor. This is the Q psi s. This is the band gap for the material, and this is the Q phi f thing. The difference between the intrinsic Fermi level and the semiconductor Fermi level. So, so this is our oxide. Let me write it over here. This is our metal, and this is our semiconductor, and that too p type. And this will be the barrier, SiO2 barrier for holes. Okay, this is the simple condition for the uh, ideal configuration. Ideal configuration for phi m equal to phi s. Okay, so this is considering the phi m equal to phi s only. Now, if we now say that, which is the more realistic case, if we now say that we are having some phi m which is greater than the phi s, then what would happen is we will be having some band bending on the semiconductor side, because the Fermi level has to align, and the equilibration or the thermal equilibrium has to be established. And as a result of this thing, if we consider now non-ideality, considering now the non-ideality like considering now non-ideality like work function difference, that is phi m is greater than phi s. Okay, if phi m is greater than phi s, then what would happen at the interface is that there should be the transfer of electrons from the so what would happen is, for phi m greater than phi s, there will be a transfer of electrons from the uh, semiconductor to the metal side. Ideally that should happen. Okay, because we want to equilibrate the system. Okay, we have to equilibrate the system, we have to have the same Fermi level throughout. So what would happen at the interface is that the interface will now be the oxide semiconductor interface will be now depleted of the electrons, and there will be accumulation of the holes, because the surface has got some reduction in the electron concentration because of the equilibration process that has happened. The semiconductor Fermi level, since it was above the Fermi level of the metal, they in order to have the thermal equilibrium maintained, we will be having the carrier transfer from the semiconductor to the uh, metal side. Okay, there will be no band bending in the metal, because it's uh, almost having it is having all, I shouldn't say almost, it's having sea of electrons. Okay, it's having lots of electrons. So what happens is simply is that we have this metal. If this is our vacuum level, sorry, and this is the metal work function. This is the metal work function. we will be having the Fermi level on the semiconductor side. It will be straight also, okay, but what would happen at the interface will be more p-type now, because it has given electrons to the metal, okay. So if this was the normal case, then this is how it would look like at the interface, considering this as EC, and the vacuum level will follow, okay. This will be vacuum level, and this will be the band bending in the oxide. And let me draw the vacuum level over here so that there is no confusion, okay. So the vacuum level will be like this, okay. Sorry for the scale is not up to the mark, that's why you must be having some confusions over there. So let me draw it like this. If this is the vacuum level, this is the conduction band, and this, since this is our oxide and there is no charge inside the oxide, that's why the electric field will be a straight line, okay. That's why the electric field will be a straight line inside the oxide, okay. This is EV. So the electric field will be in this direction for the oxide. Similarly, ES will be in this direction, pointing towards the interface. This we have seen that how we find the electric field from the band structure, okay. This was one of the problems we solved previously, okay. So this difference for this case is simply Q times phi m minus phi s, okay. So now this is kind of an accumulation, okay, accumulation of holes. So what we can do is, in order to attract the electrons to the interface, in order to have the flat bands, okay, what we can do is we can apply some voltage, okay. We can apply some voltage at gate. If this is our metal Fermi level, okay, we can apply some voltage and it should be positive voltage. So if we apply some VFB voltage, VFB1, which is equal to this difference phi ms, and we will be having flat bands, okay, flat bands, because now what would happen is we will be attracting the electrons towards the interface, and as a result of this thing, the Fermi level of the metal will moves down the Fermi level of metal, okay. So as a result of this thing, we will be getting the bands to be flat, because now we have attracted more electrons towards the interface, and as a result of this thing we will be getting no band bending, because now we have the can say the, since considering the what you can say the oxide to be having zero charge inside it, the positive voltage will impact the semiconductor such that it will attract the electrons towards the oxide semiconductor interface, and we will be having total band bending to be 0, okay. So it will be named by the name of VFB1. Similarly, we can have if we consider the oxide charges only, okay. So if we consider the oxide charges only, so if this is another kind of non-ideality, that is oxide charges only are present, so what would happen is, if I draw the vacuum level, sorry, the Fermi level of the metal with respect to the vacuum level, This will be the EVAC. And I know that the semiconductor, the oxide is having, let's say, positive charges at the interface. Okay, it is having positive charges at the interface of the oxide semiconductor interface. So as a result of this thing, this will be the positive charge, and this positive charge will attract the electrons, and the electrons will be attracted towards the interface, and the surface will be more n-type. Okay, so if this is the intrinsic Fermi level, this will be the conduction band edge, this will be valence band edge, and as a result of this thing, we will be having field towards the semiconductor side itself, and this will be the vacuum level on the semiconductor side. Okay, so because of these positive charges, we will be having negatively charged acceptor ions. So this is because of due to oxide charges. Okay, this is due to the oxide charges. We are having the negatively, you can say, the negatively charges, acceptor charges that are being built up at the interface, and as a result of this thing, we will be having the band bending. Now, in order to remove this band bending, what we need to do is we need to apply some negative bias at the metal side. If we apply the negative bias on the metal side, we will be having some voltage built on the metal side, and the band structure will look like this. Okay, this will be the negative charge, and this will be the positive charge that will be built up. This will be positive charge, this will be positive charge, and this, the bands will be flat in that case. Okay, and this will be the electric field in the oxide at that time. So this will be due to application of VFB2, and this VFB2 is negative to counterbalance positive oxide charges. Okay, so in total we can say that this in order to achieve the flat band voltage, we need to have this VFB1 plus VFB2. Okay, and VFB1 was simply given by the relation which was phi ms, and VFB2 is simply minus Q times oxide charge per unit area divided by C ox prime. Okay, because it is associated, VFB2 is associated with the oxide charge. Okay, so we need to counterbalance the oxide charge. There must be one question, why I have taken the oxide charge to be positive? Because it has been seen that for most of the cases that the mobile charges are caused by the Na positive and K positive, that is potassium and sodium ions. Okay, which causes this kind of a thing. It was more generic problem or more disastrous in the initial days, and it has been somewhat kind of stabilized in the we can say in the current technology devices. So that's why I have taken the oxide charge to be positive because it was the sodium and the potassium ions mostly that contributed to oxide charge. So what we have seen is that this flat band voltage has two components. One is due to the metal work function, metal semiconductor work function difference, and other is due to the oxide charge which is present, always present in the at the this interface. We mostly take it at the interface, however it can be distributed throughout the oxide as well, but for the sake of we can say for the sake of ease or for the sake of convenience, we take it to be at the interface. So I guess we shouldn't start with the problems of the MOSCAP because the deadline is not over yet. So uh, I guess that is it from my side for today, and if you have any query, you are free to ask. And if there are no queries, we can end today's session, and hopefully we'll meet uh, in the next live session, which will be next Sunday at the same time. So I guess we can end the session. uh, Thank you for joining today's session. Thank you.